Welcome to the International Tire Exhibition and Conference organized by Rubber and Plastics News. I am Walter Waddell, ITEC co-chair, and have the pleasure to introduce our next speaker, Mr. Christopher Napier. He received his bachelor's degree from the Toronto University and began his career with Westinghouse Polymers Electrical Division. Chris has more than 30 years of experience in the rubber and plastics industry and is a member of the Rubber Division of the American Chemical Society and of the ASTM D11 rubber and F9 tire committees. He also is retired from the military after 23 years of active Army and Army Reserve duty. Thank you for your service to our country, Chris. Chris is currently a senior applications development engineer with ExxonMobil Chemical Company in Texas and is responsible for tire technology and product testing for Butapolymers technology. His presentation this morning is Sports Utility Vehicle and Light Truck Radial Tire Survey. And now, Chris Napier.
Thank you very much, Walter. So I'd like to thank the ITEC conference for allowing me to speak, and also my employer, ExxonMobil Chemical Company, for sponsoring this project. So first, I would like to go, the title is the SUV Tire Survey, and this survey, we've done many surveys in the past, mostly with passenger car tires. We've done a couple with TBR truck tires, but this will be the first one. We wanted to look at a more specific group of tires in an ever-growing market segment with the SUVs. So tire identification, the size of tire for this survey was a 265/70R17 SUV tire. And the reason for looking at the SUV tires is we look at 2015 through 2020, you can see the growing segment of the SUV market as it increased over sedans, not only in the United States, but also globally around the world, and increased demand in all regions and global market share for the SUVs. So the 265/70R17 OE tire fitments, and also that would relate to the replacement tires as well. It was that was the number one, number two, or number three OE or replacement tire size 2014 through 2019 for all SUV type vehicles and light pickup trucks. And you can see here, these are not just a part of the OE fitments for this particular tire size, which also includes the number one selling vehicle in North America for 38 years in a row, which is your F-Series pickup trucks by Ford. And that would also include the Lobo here, which isn't highlighted. So the summary of tire identification for SUV tire survey, 22 tire sets purchased in the United States. All these tires were purchased in the U.S. Tire costs range from $97 to $220 with an average cost of $150. And as I already stated, the 265/70R17 is the top OE tire or replacement tire for SUV type vehicles 2014 through 2019. And probably also, we don't have the data yet for 2020. Tires all purchased in the U.S. were manufactured in 9 different countries. 6 were manufactured in the U.S., 4 in Thailand, 3 China, 2 Mexico, 2 in South Korea, 2 in Indonesia, and 1 tire each from Chile, Russia, and Vietnam. One note of importance is none of the tires in the survey, although there were Japanese tire manufacturers within the survey, certainly there were no tires that were actually manufactured in Japan. All tires were UTQG approved as required by U.S. law. We bought 5 tires per set of tires of the 22 different manufacturers, same production date within each tire set. And we used tire costs correlated to region, manufacturer, and company rank, which we'll look at next. All tires had 2 polyester cords, 2 steel belts, and a nylon cat ply. So these are the 22 different tire sets. This is the 2019 published rankings, and the 2020s aren't out yet, or they will be maybe by the time this presentation is made. But you can see there by company rank, number 1 Bridgestone, down in this case 39 to Century Tire. There were 4 missing tire companies in here. There was number 14 Apollo, 15 MRF, number 23 Tire Company, 24 Titan, of course, because they don't make that particular type of tire in 25 triangle. The missing companies were omitted because they didn't make this particular tire size, or if they did happen to make this tire size, it was not a tire size that was available within the United States. So you can see here we have the company, the brand, the model of tire, the location of manufacture, the manufacturing date, UTQG, and also on the extreme right-hand column, you can see the cost per tire. So in order to make sense of this, we divided the companies into tier groups. And you can see here we have tier group number 1, and this is a well-recognized way of looking at the different companies. And this has been utilized by different presentations and publications. And you can see that the number 1, which makes 45% of the tires in the world, are the first 4 tire companies, and we're calling that tier group 1. Tier group 2 is the next 7 tire companies, which make approximately 20% of the tires globally, and that's your next 7. So that's our first 11 tires. And the next 11 tire sets are going to be what we call part of group 3, and that would be anything above the 11th tire company, and they may account for about 35% of the tires manufactured globally. And once again, at the bottom, you see the tire companies that are missing because we could not obtain that particular tire size within the US. So now we're going to do a statistical correlation of cost by tire company tiers. And so you can see here on your x-axis, you have tier 1, tier 2, and tier 3 tire companies. These diamonds here, which are your means diamonds, are proportional in width to the size of the group for which they represent. And then the height has to do with the significance, the statistical significance. And then the mean is the average here, and then the gray bar is the mean for the entire group. And then across from that is the circle, which represents that group for which they're associated with. The more circle overlaps, the less statistical difference and variation that there is within that group. And you can see tier 1 here, as a reminder, is 1 through 4, tier 2, 5 through 11, tier 3 is those that are grade 12 and greater. And tier 1 tires are 35% premium over your tier 2 and tier 3 average pricing. So there's not a lot of difference between your tier 2 and tier 3 group, but you can see there's quite a premium for your tier 1 tires. The overall average for all tires is $150. So now we look at statistical correlation by cost by region manufactured. So we had 12 tires that were manufactured in Asia, and we have 10 tires that were manufactured in the rest of the world here. And you can see that tires manufactured in Asia are 25% less expensive than those manufactured in the rest of the world. Once again, the average for all tires is $150. So there's quite a statistical difference between tires manufactured in Asia and the rest of the world. So UTQG tread wear by region manufacturer, you can see that the average UTQG for all tires within the 22 tire group is 635, but tires manufactured in Asia are 23% lower UTQG than those manufactured in the rest of the world. Now, even though we looked at almost every type of correlation within this, just because we don't show it doesn't mean necessarily that it wasn't evaluated. So UTQG tread wear by company tiers. So we look at once again, the average UTQG was 635 for all tires within the group. And you can see here, this is your tier 1 group, tier 2, and tier 3. That although it wasn't really statistically significant, the differences between them, you can see there's an obvious trend between the tier 1 tire companies tend to have a much higher average UTQG tread wear than did tier 2 and tier 3 companies, but there's a trend within all groups. Next, look at tire inner liner properties. So this is an example of an isotherm TGA curve that we use to do a TGA analysis for inner liner composition analysis for all tires within the survey. In addition to doing a TGA of the composition material of the inner liner, we also did inner liner gauge analysis. And inner liner gauge analysis goes from toe to toe all the way around the inside of the tire. We also look at not only the inner liner gauge, but also the cushion gauge. and we establish an average gauge for both the cushion and the inner liner. It's measured every 2 centimeters from the toe all the way up to the shoulder, once at the center from the second shoulder all the way down to the toe again, and that gives us 25 different measurements. We record the maximum and minimum. We determine penetration flow of the inner liner between the carcass cords and do a profile analysis. And the inner liner gauge significantly impacts the inflation pressure loss rate of the tire, which we'll talk about in more detail. So here's an example of inner liner gauge analysis micrographs, 50 magnification. This is the inner liner you can see here, and I think you can see that on the screen. And then also, in addition to the inner liner, you can see the cushion layer. And this evaluates the important attributes of tire inner liner gauge and uniformity. So the summary of our tire inner liner properties: all 22 SUV tires contain halobutyl in various amounts in the inner liner with an average halobutyl content of 85 pHr. 5 of the tires had 100 pHr inner liner content. 3 of the tires were 90, and so on. And you can see we had one tire with a 62 pHr. Natural rubber is always a secondary polymer in all the inner liner formulations. All 22 tires contained carbon black with the average carbon black content of 66 pHr. 6 of the tires contained calcium carbonate calculated from TGA ash at 790C. Inner liner gauge varied from 0.48 to 1.14 millimeters, with the average for all tires of 0.8 millimeter. 14 tires had full toe-to-toe inner liner coverage, which meant that 8 tires did not have a full inner liner coverage all the way from toe-to-toe. Liner cushion construction varies very significantly. We had 10 with bead to bead, 6 with shoulder strips, shoulder crown to shoulder, bead to shoulder, and no cushion at all in 3 of the tires. So the cushion gauge varied from 0.13 to 0.89 in those tires that did have a cushion gauge, with an average gauge of 0.54. So the inner liner properties. So we had carbon black by company tiers, and you can see there's not a very significant difference between tier 1, tier 2, or tier 3 companies for carbon black content. And we also see that the inner liner gauge by company tiers wasn't very different either. Not a lot of difference between tier 1, 2, or 3 tire companies when it came to inner liner gauge. Where we did see a big difference was in halobutyl content by company tiers. So you can see that tier 1 tire companies, those 4 companies, had much higher halobutyl content than did our tier 2 and tier 3 tire companies. And IPLR by company tiers. Now we'll look at inflation pressure loss rate in much more detail in the next section, but you can see that the halobutyl content is directly related to the inflation pressure loss rate, and tier 1 companies had a much higher halobutyl content, which was directly related to their inflation pressure loss rate. And inflation pressure loss rate is how well does the tire hold air over time. No tier 1 or tier 2 tire companies use calcium carbonate. 6 of the 11 tier 3 companies did use calcium carbonate. So we look at an analysis of variance, inflation pressure loss rate model here. So what were the big factors in the inflation pressure loss rate? And those were halobutyl content. Your halobutyl pHr was the number one affecting your inflation pressure loss rate of tires. And the next was inner liner gauge. And so inner liner gauge was a secondary importance when it came to how well tire holds air over time. Halobutyl rubber and inner liner gauge are statistically significant when it comes to inflation pressure loss rates. So in the next part, we want to look at tire weight. So the weight of the 22 tires varied pretty significantly from a low of 15.7 kilogram to 20.8 kg with an average of 17.8. 5 tires were less than 17 kg and 2 tires were greater than 19.8. There was no correlation to region manufactured or the rest of the world when it came to tire weight. Statistical analysis shows tire weight qualitatively correlated to tread depth, and there was no correlation to presence or type of inner liner cushion. No other tire properties were measured. So the important thing was there's no statistical analysis that shows a weight qualitatively correlated to tread depth. Three tread depths were measured. We found 11 30-seconds in 5 tires, 12 30-seconds in 14, and 13 30-seconds in 3 of the tires. And 5 of the tires with the 11 30-seconds tread depth among the lowest weight tires, and we'll look at that. So here's tire weight, and you can see here that the heaviest tire was 20.77 kg, and the lightest tire in the group was 15.7 with an average of 17.81. And over here on the right-hand column is our tread depths in 30 seconds. Statistical analysis of weight by region manufactured. The average weight, as you see here again, is 17.8 kg. And we look at it by region manufactured, and there's just no statistical correlation, but there's a wide range. As you can see, although there is no statistical correlation between the difference between Asia or the rest of the world, there is quite a wide spread of weight differences between those tires manufactured in Asia. So again, look at statistical analysis of weight by company tiers. Once again, no real statistical correlation, whether it be tier group 1, 2, or 3. So where is the difference in weight? Where can we find that there was a connection between weight to any of the other properties? And where that was in tread depth. So you can see that although the average weight was 17.8, that when we look at the tread depths, 11, 12, and 13 30-seconds, that it was a very strongly correlated tread depth to tire weight. So tread depth closely correlates to the tire weight. So that's an important thing as we start to look at rolling resistance later on as well. Tire weight very closely connected to tread depth, and the tire weight and tread depth very closely connected to rolling resistance. So tire inflation pressure loss rates, and that's measured according to ASTM F1112, and is expressed as a percent loss per month. And when that's measured, and here's a summary of the ASTM F1112 overview. So the tires are pressurized to 240 kPa in a 21 degree C room, and that's the average room temperature. We also measure the barometric and atmospheric pressure within the room. The machine automatically records that every hour for 42 days. So we do that for 6 weeks, and then it's reported as a monthly loss rate. So what IPLR with this ASTM F1112 test does is it measures the ability of a tire to retain inflation pressure over a long period of time. It's a well-recognized test. So tire inflation pressure loss rates, the industry standard, we use the ASTM F1112. IPLR is expressed as a percent loss per month. And then we see that it varies quite a bit. The lowest tire within the group had a 1.8% loss rate per month. The highest tire within the group was a 3% with an average of 2.4%. And we'll look at that statistically to show that 4 significant variables, but only 2 decreased the inflation pressure loss rate. And that was halobutyl, as we've already seen in interliner gauge. Inflation pressure loss rate correlated to both region manufactured, and we'll look at that, and to the company rank. And then we'll look at the ISO 28580 rolling resistance test, and we'll see that it's directly linked to tire inflation pressure. And tires can lose 20 to 30% of their inflation pressure over 6 months, if not reinflated during that time. Change in pressure correlated to the manufacturing company rank. So this is our tire pressure here. You can see that the lowest inflation pressure loss rate was 1.8, 1.9% there. We had 2 tires that were under 2%. We had 2 tires that were at 3%, and the average inflation pressure loss rate for all tires within the study was 2.4%. Here we see the average pressure decrease. So in the rolling resistance test, the ISO 28580 test, the initial rolling resistance inflation pressure is 210 kPa. So if we do a calculated inflation pressure at 6 months, and we say what would the inflation pressure be 6 months later if not inflated, you see that the average pressure decreases from 210 to 162 kPa. Now here, what we have in this green column here, you can see that this is the calculated inflation pressure based on the inflation pressure loss rate as measured by the ASTM F1112 after 6 months if we've started all tires at 210 kPa. So decreased pressure has a negative impact on wear, fuel efficiency, and safety. So we look at the inflation pressure loss rate of the tires by company tiers by the ASTM F1112 tested at 21 degrees C. And you can see that the tier one tire companies are here, those top four, the next 7 tire companies, and the other 11 tire companies within the survey. So now we're going to say, well, we can look at it by region manufactured, we had previously done. But now what about if we look at by the region of manufacture in addition to the company tiers? And you can see here that the tires manufactured in Asia have a much higher inflation pressure loss rate than the rest of the world. Next is to look at tire rolling resistance by ISO 28580 test method. So this is the summary of the rolling resistance test, the thermal conditioning, warm up, 30 minutes, test temperature 25 degrees C, testing for 30 minutes, 80% of load, 210 kPa to start with, and then the speed at 80 kilometers per hour. All these tires were tested at Smithers Scientific in Ravenna, Ohio. So rolling resistance coefficient, industry standard, we used the ISO test, as I stated. We found that it varied quite a bit from a low of 8.7 kg per ton to 10.6, with an average of 9.2 for all tires. Although the United States has no government standard for fuel efficiency, European regulations for RC will look at that for comparison purposes. There was 10 Class C tires, 10 Class E, and we had 2 that were actually 2F. And then if you look at the rolling resistance after 6 months, so as we looked at earlier, I was able to show what was the inflation pressure after 6 months of standard use if they were not reinflated. We'll retest those tires at the 6-month inflation pressure and determine what the rolling resistance is if it had not been reinflated after 6 months based on the inflation pressure loss rate. And of course, the RRC, the rolling resistance, increase due to pressure loss and can be correlated to the region manufacturing company tire rank. So this is the EU tire label, as you've all seen before, and all 22 tires within the study were classified as C1 tires. And then the class over here as the different buckets. So we had C1, all were C1 tires, and then we'll look also at the class, whether it be A through F. So this is the tire rolling resistance table for the rolling resistance coefficient. So what you see here, this is the different tires here, 1 through 22 within the study, coded randomly. And then you can see this was the initial at 210 kPa. This is your ISO 28580 rolling resistance. And then here at the bottom, you can see the average for all 22 sets was 9.22. Now, if we look at the inflation pressure loss rate as related to those particular tires within the study here in this column, and then we use that inflation pressure loss rate to determine what would the rolling resistance be after the low pressure. So if we took the pressure here after 6 months, retested the tires, and then we would look again to see what would the rolling resistance be 6 months later if not reinflated. And we went from a 9.22 average, if not reinflated, to a 10.03 average for all tires. And the increase in rolling resistance was an 8.79 across the board. But it certainly was much more. You can see some of the tires with a much lower inflation pressure loss rates here, your 1.8, 1.9, only went to a only less than 3 inflation pressure percent change from its initial rolling resistance at 210 kPa to its low inflation pressure after a 6-month pressure loss. So RRC increased by an average of 8.8% due to tire pressure losses after 6 months. So the percent rolling resistance increased by inflation pressure loss rate after 6 months. This is your inflation pressure loss rate at 21 degrees C here on the x-axis for the tires. And then this is your percent change in rolling resistance after 6 months. And this is your percent change in RRC ranges from anywhere from 3%, as we saw, to as much as 13%. The average for all tires was 8.8. And the trend, as you can see, indicates a direct link between the loss in inflation pressure and increased rolling resistance. So I want to look at a percent change. And as we know, rolling resistance is directly related to fuel consumption by IPLR after 6 months. So the change in RC and fuel consumption by IPLR after 6 months is this. So if we do the calculation, we can see that the lowest inflation pressure loss rate we had within the group was 1.8%, and there was at a 9% increase in rolling resistance and a 1.2% decrease in fuel efficiency for the lowest inflation pressure loss rate tire within the group. Here we look at a 2.4. This was the average inflation pressure loss rate for all tires within the study. And we can see that the difference between the average for all tires was 12% increase in rolling resistance, which translates to a 1.5% decrease in fuel efficiency. So that's 50% more than the lowest tire within the group for the average tire within the group. And so if we look at the highest tires within the group, you can see that the 3% inflation pressure loss rate, your highest, is now 30% underinflated with a 14% increase in RRC and a 1.8% decrease in fuel efficiency. So a tire's inflation pressure loss rate has a direct impact on RRC and fuel efficiency over time. Tires with lower inflation pressure loss rates retain their rolling resistance coefficient and fuel efficiency better in use. So if we look at analysis of the rolling resistance coefficient, we can see that also we did a TGA of the tread material of these tires. And so if we look at the tread filler composition by TGA by company tier, you can see that tier 1 tire companies have a much higher silica content than do your tier 2 or tier 3 tire companies. So how does that translate if we look at rolling resistance? Well, somewhat it does. You can see here that the tier 1 companies also had the highest silica content, also had the lowest rolling resistance. And the tier 2 companies that had the lowest silica content also had the highest rolling resistance, and tier 3 companies here. Now, it's a little confounded because not only does silica just contribute to rolling resistance, but as we also talked about earlier, tire weight had a strong relationship to rolling resistance. So if we look at tread depth and tire weight, so we know that the 11 30-seconds and 12 and 13 30-seconds had a very strong relationship to tire weight. And if we look at tire weight and tread depth as it relates to rolling resistance, you can see that the rolling resistance and the tread depth and tire weight is also very closely related to the rolling resistance. But there was no relationship between tier 1 and tier 2 company and 3 companies as it was related to weight. So that's why it's a little bit masked here as far as silica goes. So if we look at an analysis of variance, so tire weight and percent silica tread filler have the greatest effect on RC. So statistical correlation weight by EU class. So if you think back to the EU label, and we look at group C, E, and F, according to the European label, we can see weight is very closely related to the class here. So the average weight, once again, 17.8 kg, and you can see that as weight increases, so does your rolling resistance. And there's a big difference between your tire weight and your, you can see here between your C and your F class as it relates. So EU class RC closely related to tire weight. So once again, we look at the RC by company tiers, and we didn't seem to find a strong relationship there, somewhat, because we remember that the tier 1 companies had the highest amount of silica within the tread formulations. But where do we find that there was the strongest relationship? And we look at it by region of manufactured. So if we look at tires manufactured in Asia and their average rolling resistance, and those manufactured in the rest of the world, we can see that there's a very strong relationship, that tires manufactured in Asia have a 25% greater rolling resistance than those manufactured in the rest of the world. So we do an analysis of variance here, using the ISO 28580 rolling resistance model. And you can see that tire weight and silica filler in the tread compound are the strongest relationship to rolling resistance model. And we'll look at the footprint pressure map as a function of inflation pressure. We'll look at rolling resistance in your actual contact areas as it relates to inflation pressure. So we started out at 110% of inflation pressure because when you inflate a tire cold pressure at 100% of the recommended, once the tire is in use, it generally increases by about 10% of the cold inflation pressure. So this is your footprint pressure map at 110% inflation pressure. And you can see here your contact area, and the red area is your highest pressure contact points within the tire. And you can see this is your tire footprint here. What we have in the graph on the upper left-hand corner is your RRC as a function of inflation pressure. That's your blue bar. And then here in the lower left corner, we see the contact area as a function of inflation pressure at 110%. So if we look at it now at 105% inflation pressure, you can see that the tire continuously grows. Not only in the rolling resistance goes up or is negatively impacted, but also your actual contact patch goes up as well. But and additionally, it also changes the location of your contact. So the graph here, the contact footprint pressure map here on the left side, you can see where we started out with a rolling resistance of 7.4. Rolling resistance coefficient than your actual contact area here. And if we look at it at 70% of inflation pressure, you can see the rolling resistance coefficients increase by 18.25% as we decrease pressure over time, and your actual contact area increased by 23.25%. But additionally to the increase of the contact area and the rolling resistance coefficient, you can see that this is a good pressure distribution here on the tire that's fully inflated. But if we look at the change in pressure distribution, you can see that what we have is where the pressure had been pretty well distributed around the entire footprint. Here we can see that almost all the pressure now shifts from the center, so we have very poor wet traction here, good wet contact here in the middle of the tire in the crown area. But what we see is most of that is now shifted out into the shoulder area, which is going to give us poor traction and also poor tread wear. So observations in summary, there's a strong relationship of price to company tier and region manufacturers. Tires manufactured in Asia had a 23% lower UTQG tread wear than tires manufactured in the rest of the world. Tire weight was not correlated to company tier. Tire weight is strongly correlated to tread depth, which is also very strongly relationship to rolling resistance, as you may remember. Halobutyl rubber content in tire inner liner correlates to the company tiers. Inflation pressure loss rate is correlated to halobutyl content in the company tiers and region manufacturer. Lower weight tires had a lower rolling resistance. Tires manufactured in Asia had a 25% higher RRC than those manufactured in the other parts of the world. Tier 1 tires had a lower average RRC. Tier 1 tires exhibit higher price, longer tread wear, lower inflation pressure loss rates, and lower RRC with higher halobutyl content in the inner liner. And inflation pressure directly impacts footprint, rolling resistance, tread wear, wet traction, handling, and energy efficiency. And for your attention, I thank you very much.
Thank you, Chris, for your very interesting presentation. I would also like to thank our audience for attending this session of iTech and our sponsors for supporting iTech Virtual 2020. If you want to revisit this session or any others from this conference, they will be available on Rubber and Plastics News website, rubbernews.com, after the event is completed. If you would like to purchase papers from this or other sessions of iTech, visit itech-tireshow.com to do so. Also, you can connect with your colleagues here through the virtual networking program, which can be found on the left-hand side of your screen. Simply click the Meet icon to start connecting with fellow iTech attendees. Again, thank you all for joining us this morning. Goodbye.